Hey everybody, this is Steve with FrSky, and today we're talking about the beautiful world of protocols, warnings, and transmitters and receivers. We're talking about all sorts of this technical stuff, and I'm hoping I'm going to put it together in ways that's understandable. This is going to be highly simplified. I do apologize in advance, especially if you have an advanced degree in mechanical or electrical engineering. This is for people to just get what we're talking about when we talk about these terms. Okay, first and foremost, we're looking at the beautiful world of zeros and ones. This is the basic, the lowest common denominator in the computer technology. Entire empires are set up on zeros and ones, and that's how things are transmitted from the transmitter to receiver. It's a long string of zeros and ones. And right away, I'm going to make a confession. For the last couple of years now, I've been lying my teeth out to everybody. My gosh, I really need to go to confession because I've lied to everyone I've met, and I've told them our receivers are 24 channels, our transmitters are 24 channels. Every single one of them, including the X14, is 24 channels. Boldface lied. Shame on me. The truth of the matter is, it's one channel. However, in that one channel, are 24 channels. So the way to think of it is like this. You have a moving truck. A moving truck has 5 rooms worth of furniture in it. Is it a 5-room house or is it a moving truck? By the time that it gets to your house and you unpack it, it's a 5-room house. Even though the transmission process is in one truck. So same thing. What we have is a tremendous long stream of zeros and ones going from the transmitter to the receiver in the plane here. And there's so much information coming so quickly that your plane doesn't even need all this information. It's far more than it can possibly use. However, we send it out anyways. So what happens is the receiver in the plane unpacks all this information and populates those 24 channels. And it does other things you might not even know about. For example, your sliders, your switches, and your knobs are all being monitored while you're flying. Even if you're not using sliders, even if you've never used a slider in your life, you will have the information being broadcast many times a second about where the position of that slider is, even if you're not using it. So lots of information is being transferred. Some of it goes missing, and the big thing is we're not going to worry too much about the stuff that goes missing. We're going to talk about valid frame rates, but in order to talk about valid frame rates, we need to talk about frames. And what is a frame? A frame is made up roughly of 8 channels, and we have what we called S-bus, or serial transmission, which serial means one long stream of zeros and ones. They do either, our default is 2 frames, and we have the option to do 3 frames. And as we get to 3 frames, you have a bit more latency because it takes longer for transmission to go from the transmitter to the receiver because it's waiting for the last set of 3 frames to come through. Now, I hope this doesn't look bad because okay, try this again. This is where things get interesting. The transmitter and receivers, the way they work. The transmitter sends after a certain amount of time, it sends a reset and it says, hey bud, I sent you 100 frames, what did you get? And the receiver calculates and says, I got 90 frames, so 10 frames went missing. And you will know about this because it sends back information. Now, the term transmitter and receiver are kind of a loosely used thing these days, in my opinion, because the receiver actually transmits information back to the transmitter through a process known as telemetry. And one of the pieces of information is this VFR, valid frame rates. And what that really means is link quality, because when it gives a number, when it says I got 90 out of 100 frames, that means I'm getting most of the frames that the transmitter's sending out, 100 frames, the receiver's getting 90 of those frames. So even though it's lost 10 frames, it's still very high link quality, and that's what we look for. And you'll start to see over time as you fly further and further away, it'll go to 70, 60, 50, 40. And then sometimes people are very concerned, like, oh my God, I had a link quality of my VFR was 60. That's horrible, right? No, no, no. I mean, the kind of stuff that happens from time to time, especially on 2.4 gigahertz. So what we try to do is strive for higher numbers. And once again, I hope that here we go. I'm going to use an example. This is a famous series of photographs that were put together to create the illusion of a horse running. So this is from the 1800s. You can see there's 16 frames here. But as they were displayed, if you look at them, it looks like the horse is galloping. This was the start of the motion picture. These are 16 different frames, but when they're put together quickly, the horse is moving. And in motion picture terms, the most common frame rate these days is about 24 frames per second. I mean, you can go much higher, up to 1,000 frames per second in today's technology, but a lot of movies are filmed in 24 frames, and the idea is that as you see all this running one after another, it gives the illusion of fluid. You know, the horse galloping, things are fluid. It doesn't look jerky or anything else like that. And the same thing kind of happens with a transmitter as well. It sends out a lot of frames. Let's just imagine that these are all frames, A to Z. There's 26 packets, so it's roughly, let's say, 1 second. And A is throttle all the way down, it's at negative 100, and Z is throttle all the way up to positive 100. And you had a nice 1 second ramp up from zero, or throttle down to all the way up. And if you listen to it, you hear a nice smooth transition, you know, picking up. What would happen if all of these were missing, and all you got after 1 second is you had A, and then a second later Z? Well, what would happen is there'll be no ramp up. It would go right to full throttle. Boom, instantaneous full throttle. And, you know, that's probably not, that's not really the way you want to fly. It's not really great for the plane. It puts a lot of stress on it. You want to have a nice ramp up. So you want to go through all the letters. But occasionally, as you're going through all these letters, the C might get dropped, and the L might get dropped, and the U might get dropped. But it happens so quickly you won't even notice it. And that's the whole idea about drop frames. You can lose frames, and it's not really going to affect the way that your plane flies. Do drop frames equal peril? And not really, because there's a lot more frames being broadcast than you actually need. So you drop a few here and there, it's not so bad. We start to worry when you get to the point where you're down in the 40s. If you're only getting 40 out of every 100 frames, you're going to start to get a low VFR warning. And so that's when you get the low VFR warning, it's time to take the plane and turn it around to some place with better radio range. All right, we're going to switch gears now. We're going to talk about the transmitters. What do we have here? We have the beautiful and my personal favorite X20S Cardinal Red. I had something to do with that story, so I've always loved that transmitter. Had nothing to do with the X14 and this green. Some people really love that green. That's all I'm going to say about that. All right, we're going to talk about FSK, and that stands for Frequency Shift Keying. This is a technology that came out. So back in the old days, you talk to the old timers at the field, they'll tell you the stories about flying on 72 megahertz, and then all of a sudden this 2.4 gigahertz FSK came out, and it was like the best thing that ever happened to RC, because back in the old days you used to have to fly, if you would be like channel 36 on your 72 megahertz and someone else had channel 36, you would go and you would pull a pin at the field and you put it on your transmitter to let people know that you had pin 36 and they can't fly as long as you're flying. They can't even turn the transmitter on. If they turn the transmitter on, even for a brief second to check something out, your plane would crash. So This 2.4 gigahertz FSK was mind-bogglingly good, and it is absolutely, really one of the more stellar, amazing technology to this day. They have something called Flight Fest in Ohio every year, and they get hundreds of people flying on 2.4 gigahertz at the same time. So it's a big party. Everyone can fly on 2.4 gigahertz. It's a wide open channel. Lots of good things to say about it. That's why you see manufacturers like Futaba, Spectrum, and Powerbox. They love this stuff. It works great. The only problem we've run into is not the problem with the hardware. It's the problem with the actual RF environment. It's gotten worse over time, actually much worse over time. So there are things out in the fields occasionally, like for example where Flight Fest is located at, there's an oil well out there that about every 10 minutes or so it broadcasts on 2.4 gigahertz how much oil it happened to pull up, and if you happen to fly through that signal as it's being broadcast, it swamps the plane and down she goes. So that's called signal swamping. That's one of the problems. So it might happen for a second or two, but it might be the difference between flying and not flying your plane anymore. So what happens is there's this new technology over the last, it really started to become popular around 2016. We call it LoRa, long range, and the first one that came out was 900 megahertz. That is a shorter frequency length, and it is, right now, it's kind of the industry standard as far as long range transmission protocols, or transmission, the way that the way things are transmitted. 900 megahertz is really one of the best out there. The problem with it is that you can't have hundreds of people flying at like 2.4 gigahertz. It has a very limited amount of channels, so it's not for everybody. But the idea behind it is that it penetrates exceptionally well, and it penetrates behind trees, around buildings. It does a fantastic job of getting into places where 2.4 gigahertz FSK just can't get to. And a new technology came out, which is called 2.4 gigahertz LoRa, which is very similar. Even though it's 2.4 gigahertz, it's different than the FSK. It's a long-range protocol. It has become popular over the last few years from the open source community, and FrSky has really taken this technology, improved upon it. We have 24 channels. It's a closed source technology, and it works exceptionally well. Not quite as good as the 900 megahertz, but it is very similar. So let's see. Here we go. Tandem 2.4 gigahertz FSK and 900 megahertz. And essentially I wanted to point out is that there's two different receivers in one receiver. This is a 900 megahertz receiver antenna, and this is a 2.4 gigahertz receiver antenna. So inside of this one package are two different receivers. And what happens is the transmitter transmits both 2.4 gigahertz and 900 megahertz at the same time. The receiver receives both of them at the same time, but it prefers 2.4 gigahertz because it's that wide open party transmission. And essentially what will happen is that if the 2.4 gigahertz happens to just drop for even momentarily for a second or two, what will happen is the valid frame rates will start to drop down to around 30. The receiver says, oh my gosh, I'm losing frames on 2.4 gigahertz. Well, look over here, I got 900 megahertz. I'm going to fill in with 900 megahertz, even if it's for a couple seconds, even if it's a turn. The places why I find planes to be most vulnerable is when you're coming in for a landing, you're on final approach, you're turning towards the field, you're close to the ground. The plane has its wings turned, it's close to the ground. That's where you're going to lose reception on 2.4 gigahertz. It's very vulnerable at that point. 900 megahertz fills in because it's a long range protocol. It goes much further than you can see. So essentially, it might be that savior for a moment or two, just a few brief seconds, but you'll get your plane back, you'll get through, you'll land your plane, and you might not even notice because when you're flying at 900 megahertz, it flies identical to 2.4 gigahertz. The only way you'll know that you were on 900 megahertz is by going back and looking at the telemetry logs. Okay. And twin is like tandem with 2.4 gigahertz. So it is, as I mentioned before, it's the 2.4 gigahertz long range. Instead of having 900 megahertz, it's 2.4 gigahertz FSK and 2.4 gigahertz long range. Because the antennas are smaller, it's great for drones and gliders. Similar performance to 900 megahertz, not quite on par. And we made this with a specific market in mind. I'm hoping you're not seeing this flicker, but on my screen it has. So there's a new protocol that's coming out right now called Tandem Pro, and it is all of these. It's 2.4 gigahertz FSK, 2.4 gigahertz LoRa, and 900 megahertz. We're only going to make it for a couple very high-end receivers, and so far the only transmitter that transmit on this is the X20 Pro. The X20 Pro will broadcast to every receiver we sell right now. So it'll work with Tandem, it'll work with Twin, it'll work with Archer. Speaking of Archer, this is our oldie but goodie. So 2.4 gigahertz, that's where FrSky got its start in 2010, was a 2.4 gigahertz transmit and receiver module. We didn't even make radios at the time. And the idea behind it was that the receivers had, actually I'm missing something when I look at this. Here we go, try it again. Had something called access. At the time it was ACCST. It was ACCST V1 at the time. This is a long time ago. And this was a very, very good transmit protocol, and people loved it. It was superior to just about anything out in the field at the time. And what happened was we started making transmitters that were on ACCST. Then over time, we had to do a lot of adjustments, and people were concerned that they weren't seeing the firmware on their transmitters anymore. So we moved from open source to closed source technology. And we started working with something called Access, and that was a closed source technology. And that one had a lot of improvements, including the ability for people to see what firmware they were on. And over time, we had something called Archer, and then because of the chip shortage in 2020, we had to change it around to Archer Plus. Archer Plus was an improvement over Archer because it had better RF interference reduction and it had spark arresting technology. Back in the day, we used to have we had something called the Archer Pro line of receivers. So the SR10 Pro was a receiver that had spark arresting technology in it. Now all our receivers have spark arresting technology, including the Tandem line of receivers as well. So the other thing that's interesting about this is that you have the ability to you can bind to it with Access, or you can bind to it with ACCST V2. So even our transmitters from 2014 with an ACCST V2 update can bind to our newest receivers. That is really innovative. And finally, what I'll discuss here is that what you should really do when you're looking at how you can avoid issues with low VFR is a lot of it's dependent on how you mount your receiver antennas. The excuse me, the 900 megahertz T antenna, this should be laying flat on the ground or above on the top of the fuselage, going left, right. I don't have it going the length of the fuselage. I usually just have it go left, right. It does not point to the sky and the ground. And the 2.4 gigahertz antennas should be One should be going the length of the fuselage, the other one should be pointing up and pointing down. The thing I'll point out is that the white part are the only part of the antennas that broadcasts the signal. So you can tape this to something and then drill a hole in your fuselage and have the whiskers stick out the top of it. And then the other thing I'll mention is satellite receivers will work with this. You can hook up, for example, on this TD-SR18, you can put on a TDMX, a TDR10, TDR6, whatever you feel like. In pin 1, you change that to S-Bus in and you use S-Bus out on those other receivers. It all works, and you can get a satellite receiver. The only downside with that is that when you do it with 2 receivers, what happens is you only get the telemetry from 1 receiver. So there's a risk of doing that where you can have a whole flight with no telemetry because the receiver, like the TDMX, can grab a hold of the signal first and then not give it back to this TD-SR18, and what you'll get is no telemetry for the entire flight or a part of the flight, and it's very frustrating. So before you go down the road, and I know a lot of us have grown up with the idea that we need to have satellite receivers. You have built-in diversity with these receivers, not really super necessary. I would try to do without them first of all, see if you can get by with just one single tandem receiver. Chances are it will work fine. And if you really need it, it is available. You also might want to consider using something like redundancy bus if you want to use multiple receivers. So the RB25, RB25S, RB35, and RB35S might be good things. Last thing I'll mention is be sure to turn on telemetry logging. And that is it. Hope you guys have a great day, and thanks for watching. If you have comments, please leave them. Questions, please leave them in the comments. Thanks.